Good evening, everyone, and welcome to Astronomy at the Beach 2020. I know it's a virtual event. It's a bit weird for everyone, but we're doing what we can. So we're about to start another event with the Ford Amateur Astronomy Club members. And in this event, we're going to have Mike Bruno, who's our club president, to talk about the size and scale of the solar system. Just before Mike gets started, I want to give you a heads up of what else we have coming on for the rest of the evening. So we have many events. So if you go to glac.org, you will see a full schedule of events, but specifically the Ford events. After Mike is done talking about the size and scale of the solar system, at 8:30 we'll have Tim Campbell and myself coming on to talk about spectroscopy and how we use light to analyze and learn about what the universe is made from. And then following on from that, we will have a live recording of the Astronomy For Everyone TV show, which will be with John McGill, who is one member of our club. And John will be talking about NASA rocket launch photography. And then once that event is over, at 10 o'clock, we will then go over to Gordon Hansen, who will, based on weather, will either go live viewing from his telescope in Woodhaven here in Michigan, or if it's overcast, and it looks like it actually might be, he will actually go through the processing of data for processing of images that he takes with his telescope and process them into the beautiful images that we all love and see. So I'd like to hand it over to Mike now. Take it away, Mike.
Thanks, Liam. So yeah, welcome. I appreciate whoever's out there watching tonight. I gave a presentation yesterday, and it is on our Astronomy for Everyone YouTube page. And tonight's, of course, will be different because I winged it last night, and I'm winging it tonight. But I've talked about my scale model of the solar system many times over the years. I have some notes. I'm going to do a little presentation. But in front of you, here is my model. I was always interested in the size of our solar system and the distances and how big everything is. So one day I got this, saw this half-inch blue marble, which a lot of people refer to the Earth as the blue marble. And I decided, well, let me just see if I can build a scale. And I went out, tried to find the exact measurements of the solar system. And then being an accountant and an Excel person, I made a little spreadsheet. And every time I change the size of something, my spreadsheet does the calculations for me. And so I went out, measured, found common objects that people are familiar with to build this scale. And the hardest thing was to find a sun so big. So we have a half-inch blue marble here, and then we have our sun, and this is basically, a lack of a better word, a 5-foot beach ball. I used to use a weather balloon at one time, and after filling it up and deflating it so many times, I guess weather balloons are really just a one-use object. It decided to go supernova, so I found something a little bit more durable here. But the scale, like to see like this big Earth we live on, and to understand like how tiny the Earth is compared to the sun. Being in person, to be able to like hold this little marble, I like to have people hold it next to the sun, and realize like, wow, this is really tiny. And because I wanted it something that you can see and hold, I can't really do distance because the distances are so massive, but we'll talk about distances in a little bit. So right now I'm going to go to my presentation, and I'll talk about a few things and some interesting facts, and hopefully you find this interesting. Let me see. Let me share my screen. Where is my screen? Oh, here we go. I'm not at the right point, so let's get up. Okay, so I gave you a little info. So sometimes they're referred to as the blue marble. So I went through my little thing, and here's that little marble, little half-inch marble here. I found some different interesting slides and things on the internet. It's great. I wish I had this display myself. I don't know if it's just computer generated, but it kind of gives you a small representation here just on this picture of just how massive the sun is compared to the rest of the planets in our solar system. Briefly talking about astronomy, it's the study of, you know, planets, stars, galaxies, and the formation of the universe. Bringing it home here, I'd like to talk about the solar system that, you know, we know and love. The planets right now, when I made this model, Pluto was a planet, and so we had 4 inner rocky planets: Mercury, Venus, Earth, and Mars, and then the outer planets: Jupiter, Saturn, Uranus, Neptune, and Pluto. And Pluto will always be a part of my scale model here, because first off, Pluto was glued down to the model you saw sitting in front of you just a moment ago. Also part of the solar system, it's kind of like the dust of the solar system. It's comets, asteroids, all the moons, and everything that orbits around our sun. That our sun really has the gravity to influence objects and keep it in its orbit out to a light year away, you know, from one direction and a light year another direction. So when we get into that, if at the end here, that's really far. I love this little picture here. It's kind of like real pictures of the planets, and it gives you a little bit of, you know, some images that you see through either the Hubble, or now some amateurs are taking amazing pictures of Jupiter and Saturn, at least, that rival some of these space telescopes. So a little bit about the sun. You know, the sun's massive. The sun is 99.86% of our solar system. Think about that is basically everything else is just leftovers. 99.86% of anything that you want to weigh in your house, or if you have like a pound of sugar or anything, that's basically all of it. So the sun is really the solar system, and the planets and everything else is just leftovers that happen to be not become part of the sun when it formed. Quick overview: the sun's very hot. The core is 15 million degrees. It's you don't want to be anything near the sun in general. The surface of the sun's 5 to 10,000 degrees Fahrenheit, and but there's something also that surrounds the sun that's called the corona, and it's I guess I should ask one of the experts on assisting me. The corona would be, is that more of the hot plasma coming off of the surface of the sun? It's about 2 million degrees, which is amazing.
Yeah, it is actually super hot, but they don't know why. They're investigating why right now. They have a spacecraft going around the sun called a Parker Solar Probe, and those who are into physics or heliodynamics are actually studying the corona or the atmosphere of the sun, the corona, to try and understand why it's so hot.
Yeah, so you want to see the corona one day too. So we had a solar eclipse in 2017. And I'll tell you, if you didn't get to see it then, plan on 2024. It's a rare event, and we might talk about that a little bit later. But
and one comment to make about viewing a total solar eclipse is you want to be in totality.
Yeah.
Do not make the mistake of going to some place where it's going to be 99 point, whatever percent. It must be 100%, or you miss the entire thing.
Exactly. I've been lucky. I've seen 2 total solar eclipses, but there's some people we know have been to quite a few, and it's almost life-changing. It's something that nature, for this unique time and this random circumstance of alignments, is incredible to witness. It's almost like, if you got to look out in the Grand Canyon before, it's one of those things that nature, it's hard to describe unless you witness it with your own 2 eyes. The sun on its surface has some sunspots, so I hope some of you were able to see the solar viewing earlier. There are cool spots on the sun that create these sunspots, and you definitely need special equipment to view the sun and look at the sunspots. So make sure you don't use anything of yours that's like a binocular or anything else. There's specialty telescopes for that, and you want the proper filter so you don't damage your eyes. This little slide here kind of shows solar flare. They kind of last just for a few minutes, but if you see the little Earth in the top right, they're many times bigger than the Earth. And there's also things, they can get bigger and they kind of arch over. They're called solar prominences. And those can be anywhere from 100, the typical is 100,000 kilometers to 500,000. So you're talking 10 to 50 times the size, the diameter of the Earth. So not only is the sun massive, everything that happens on the sun is massive, including this coronal mass ejection here. So that's that big plasma piece of the sun that it basically burped out off a little hiccup here of very hot plasma. And on that scale, I couldn't even imagine how many Earths would cross that. It's probably 50 Earths on that one. It's gigantic. The solar wind also causes aurora that you sometimes hear about in the news. Every once in a while they get down into our area in Detroit, but the further north you go, the better likelihood of seeing an aurora. It's the solar wind is crashing into the Earth's magnetic field, the magnetosphere of the Earth, and it causes these amazing colors. And they're surprisingly, with a decent camera equipment, I caught a few pictures over time myself, but they're really neat to witness. So when you hear about aurora, if you're in the area, you want to look out at the night sky and take a look at the aurora. It's almost like the sky is dancing with this activity. It's very beautiful. So the sun is massive. It's 865,000 miles in diameter, and the Earth is almost 8,000. So it would take about 109 Earths just to span the diameter of the sun. Also, a fact I like to have people guess is like how many Earths can fit inside the sun, and it's 1.3 million Earths. So if I had 1.3 million blue marbles sitting around right now, it would fill up my solar system over here of my 5-foot beach ball, which is really crazy to think about. Like 1.3 million, you're getting into numbers again that people you can't really comprehend. So also a common measurement in astronomy is called the astronomical unit, and that's the average distance between the Earth and the sun. So it tries to bring these larger numbers of 93 million miles basically down to 1. And sometimes you will hear that. Another fun fact sometimes I like to talk about is, how long would it take to drive to the sun? If you could hop in your car, you're doing 70 miles an hour. It looks like you think, oh, the sun is big, but it's, whatever, 93 million miles, you don't know. You drive there 151 years. I mean, that's just, it's hard to comprehend, like sunlight that takes about 8 minutes to get here. It would take you literally, a couple of lifetimes really to drive there. And that's just going one way on this one-way trip to the sun.
Yeah, Mike, I like to also use in a similar fashion, a 747. If you could fuel it up, and you could put enough oxygen on it to survive a one-way trip to the sun, it'd be 20 years one way.
Yeah,
sure. There is no air in space, but if you could ignore that and let it go at the speed that it normally flies, a little better than 500 miles an hour.
Yeah, you can hold your breath. It takes you 2 hours to get to Florida, but it'll take you 20 years to get to the sun.
Well, another one I came across, I forgot that I would bring up years ago when we still had the space shuttle, because this presentation, by the way, is pretty old. But the space shuttle or the space station right now, it travels about 17,500 miles an hour up in orbit. And on that scale, the traveling to the sun isn't too bad. It's 221 days. So again, it's a one-way trip. You know, you get close to the sun, you catch on fire, and you die. But at least you'll get there a little bit faster than you know, taking a car. So I always it's and but I think when you think about stuff like that, like these speeds, like oh the shuttle or space station, like they're up in orbit, they're up in space, and it's oh they're floating in space. But I sometimes have a globe with me, and if you have like a school globe, like a 16-inch globe, I'm like, well, you know, how far up do you think the space station is? And you know, people think, you know, I don't know, feet away, or you know, 10 feet, 12 feet, whatever. I'm like, no, like you put your hand on top of the globe, and the top of your fingernail is about the height of the space station. It's about between, I don't know, around 300, 250, 300 miles, maybe 400 miles altitude wise. So on just a 16-inch globe, it's like a half an inch. So it's basically you're just off the surface of the Earth when you're up in space on the space station right now, which is kind of neat. On my scale, we'll show the model again in a little bit, but the one thing you can kind of understand is maybe a size of a football field. So if you go about 2 football fields, 550 feet, that's where that blue marble goes, or the distance between the 5-foot beach ball and my Earth marble. So at least you could still see this, you know, like we see the sun. And if you did this exact distance on your feet, the sun would literally be the same size as the sun in the sky. So it's about a half a degree in diameter in our sky. You go 550 feet away, you look at my model here, that is how big the sun would look, which is kind of neat to think about. But some of the other distances, when we get to the outer planets, it gets a little bit farther, and you probably need some binoculars like we do at night just to look at the planets, which is kind of neat. The moon is our closest neighbor, so everybody likes to talk about going to the moon. And the moon is 27% of the diameter of the Earth, about 2,160 miles, which puts it, like if you put it over the United States, it would pretty much span, you know, pretty much across the entire United States. I can't remember if it's like, that might be 2,300 miles or something. But on my scale with this half-inch marble, the moon would be only like 4 millimeters. So that's the size of a BB that, you know, maybe you had if you had a BB gun when you were growing up. And also, if we're driving again to the moon, it'd take 142 days. So even though the astronauts took about 3 days, they're going pretty fast, right? So, but you know, that's the farthest distance man has ever traveled. So on my scale, it's 17 inches. So, you know, you're like, wow, we flew to the moon and landed on the moon, which is an amazing, incredible accomplishment, especially back when it was done. And of course, it hasn't been repeated since. But the 17 inches on my scale, like, wow, that doesn't seem like it's really that far, especially when we're going to be talking about some of the other distances.
The comment I'll make about the scale of the Earth and the Moon, and I use this in the planetarium all the time, is doesn't matter what object you want to use to represent the size of the Earth. If you have 30 of those objects, so let's say you decided the Earth was going to be the size of a basketball. If you had 30 basketballs, you would line all 30 basketballs up edge to edge. And then after the 30th basketball, you would need one more object that would be 1/4 the diameter, approximately, to put next to it. And now remove the 29 excess basketballs so that you just have the first one and the farthest one. And you can do this with any scale. It's about 30 Earth diameters away.
Yeah, so I guess it almost does, my math almost does that there with the 17 inches and my half-inch marble. Actually, the marble's really 0.562 inches. So, so to get exact, I was actually out there measuring with calipers and everything, trying to get these little objects as close to true as possible. I'm going to touch on the planets right now.
We have a question for you.
Oh, sure.
Question is, with regards to Tim kind of answered it, but the question was on the marble and the BB scale, how far away would the BB be from the marble?
Yes, that's 17 inches.
17 inches, yeah.
Yep.
And you don't have a zoom in for us like you did yesterday, but you do have that little model on your table in front of you.
Yeah, yeah. We will do. We'll show that. I think I might have a slide in here shortly, and then we'll go back live and zoom in on the model for the end a little bit, just to take a quick. So, I talked a little bit more detailed about the planets yesterday. So, I'd love for you guys to go look at my presentation yesterday, because each day, we talk about different facts and different things. Um, so I guess what was it? The one thing I didn't comment on the moon, let me see. Oh yeah, it's about 240,000 miles away also, just so you kind of get that thought in your head. So we're just going to touch on the planets here shortly, but sometimes I like to deviate off of the size and uh, distance for a moment, just because I found this slide doing some research, and I thought this was amazing to think about, is the scale, a different scale here with the Earth and all the water that is on the Earth. So, the Earth's 70% covered with water, and you're like, wow, that's a lot of water, and the oceans are very deep, but we're really tiny. But so if we vacuum that all up and we had this bubble, like it's crazy to think that all the water on the Earth is this size here. It's about a 2,000 mile diameter bubble of water, and that's all the water that's in the oceans, lakes, and everything. And then there's like a tiny bubble off to the right, maybe around Tennessee or something there. And that would be all the fresh water, which includes glaciers, groundwater, and surface water. And then if you go a little south there, just almost to Florida, there's a really tiny blue dot. I don't know if y'all can see it. And that's all our fresh water. Our fresh water is like just 2.5% of all the water on the earth. And that's all the ice, snow, lakes, and rivers. And I mentioned this yesterday and I forgot to look it up for today, but the Great Lakes, and that's a huge piece of the fresh water. So it's a pretty cool thing to think about, seeing that as a different type of scale model. And when you look at my Earth, my Jupiter on my scale shortly, and then the 5-foot sun, Jupiter is technically, it's the same size as this scale if my sun was the Earth. It's kind of unique that it worked out like that. And I think a ping pong ball would be all the fresh water.
Tim, actually, the scale, the depth of the oceans that you went over yesterday.
So this was something I just happened to be watching Neil deGrasse Tyson, and he mentioned. He said, if you took a globe the size of a typical schoolroom, and sometimes you see these globes and they're sort of textured to kind of show you where the mountains and stuff like that are. And he said those are way, way, way out of scale, of course. And you're thinking, well, of course it's out of scale, but you don't realize how out of scale it is. The globes that are completely smooth, those are actually much closer to the accurate scale. Tallest. So think about the size of the Earth. The diameter is 7,900 and something miles, but let's just use rounded numbers so that we can easily do this in our head. Let's just round it to 8,000 miles. That means that from the center of the Earth out to the surface of the Earth is just about 4,000 miles. The highest mountain on the planet, something like 5 miles high, right? Mount Everest, and the deepest ocean trenches, just a few miles deep. But think of those few miles, maybe 3 miles deep or whatever it is, and 5 miles high. And what is the percentage versus 4,000 miles? And it turns out, maybe about 1%. So he says, if you were to take look at very closely at your finger and look at the fingerprint that you have, the ridges on your finger, if you were to touch them to the surface of the globe and you touch them in the middle of the ocean, the ridges on your finger would touch the bottom of the ocean floor, and the grooves, right? The deeper part of your fingerprint, the grooves would still be dry. Water would not actually make it that deep. The ridges on your fingerprint would hit the ocean floor before the top of the groove would be wet. That's how thin the water is on the surface. And we think, oh, it's miles deep. No, yeah, but it's thousands of miles radius. And so when you think of the scale of the Earth, a couple of miles deep is nothing compared to the 4,000 mile radius. So the planet itself is just very smooth spherically and just barely covered with water at all.
Yeah, it's really pretty crazy to think about. how little water really is on the Earth, even though we're covered in it.
I wouldn't say we're a water planet. We're a damp planet. There's no little water on it.
Yeah. So I'm gonna touch on the terrestrial planets today, and I might go a couple minutes longer today. I want to get into like the outer planets, which I kind of skimmed over yesterday. But you see these great images of Mercury, Venus, Earth, and Mars, and at the bottom there it tells you the size, what percentage they are compared to the Earth. One thing I like to point out is Mercury's only just over 5% the mass of Earth. It's very tiny. It's actually, that planet is smaller than Ganymede, the largest moon in the solar system, which is around Jupiter, and Titan, which is the largest moon that orbits Saturn. So Mercury's smaller than that. And Mars, as much as we see Mars in the news and look at it, it's a little, like a junior planet compared to the Earth, at least. But then we are like that compared to the bigger planets. So here's a quick image of my scale model that you can see. There's the 17 inches from the moon and the Earth. And you got Mercury is a peppercorn, actually. It's just over 5 millimeters in diameter, or 0.2 inches. Venus is basically 95% of the size, so I just painted a marble. It's the same thing there. And then Mars is 8 millimeters. And that's that's a pellet right there for a wrist rocket. So now we getting into the other planets of the solar system. We got Jupiter and Saturn, the gas giants. They're gigantic. Jupiter holds all the other planets combined. Jupiter is more massive than that. So we could fit every planet and the rest of the solar system inside of Jupiter. It's crazy how big Jupiter is. I mentioned the 99.86%. Jupiter is like about another 0.13% of that. And so then you're down to like 0.02% for the rest of us. So it's crazy. Here's my model again, quick slide shot. So there's Jupiter, sponsored by Spalding and the NBA. It's a little kids basketball. For Saturn, I like to point out that this cardboard representation of the rings, it's the right scale for distance, but they're so thin, it's only a kilometer in space. Like a kilometer is like really thin when you think about it in general, but that's the thickness of it. So if I tried to do that scale on this, it would be thinner than a piece of tissue paper. And then I have a couple racquetballs here for Uranus and Neptune. And then if you can see in the bottom right, you can't really tell what that is. It looks like a smudge, but that's Pluto. Pluto's so tiny, it's just under 3 millimeters in diameter. And, we just flew by it, 2015, which was amazing. Here's another quick look from a couple years ago of my model. On my scale, Jupiter, you talk about size and distance, you get in the big numbers. So you're talking, 89,000 miles in diameter. My scale model, it's just over 6 inches for that basketball. And the distance is 484 million miles. On my scale, it's just over a half mile away. So now you're like, oh, you can do a half mile walk or a bike ride or something like that. So you aren't too far, it's not too far away. But really, you're talking this little basketball away from my 5-foot sun here. And there's a little quick representation of the Earth. And Saturn, same thing. It's a little bit smaller than Jupiter, 75,000 miles. It's almost 1 billion miles away, 888 million. And it's a little bit smaller on the scale, a 5-foot basketball, a little kid's basketball there. And on my scale now, you're talking, you got a mile. So now I talk to the kids, and if you're hopefully watching, you could go on a mile walk, or you might run a mile for gym or a mile bike ride. So it's not getting too crazy. But then again, now we're just a mile away with this little basketball. And there's another little quick Earth to Saturn view. I talked about the rings briefly. They're 175,000 miles away from the center of Saturn. And the particles that make up the rings are basically the size of grains of sugar to the size of a house. So really the particles aren't that big. On my model, that's 12 inches across. So if you hold Saturn on its side, the diameter will be bigger than Jupiter at least. And the rings are wonderful to look at through the telescope. So I hope you guys get out one day soon. We're out back with everybody with our telescopes, and you get a view of Jupiter and Saturn. It's really, really amazing.
Mike, we have a question for you.
Okay.
And it says from Samran Mooley, I believe. It says, Mike, I'm starting a space club in my high school, and we want to get speakers to come and talk about what they do. I was wondering, would you be able to come and speak at some time to our club?
Yeah. If you want to put out my email.
Well, they can email info@fordastronomyclub.com, and I will type it into the chat. And if you email there, we can work with you and arrange that.
And that email actually comes to my personal email. So yeah, please do that. That'd be great for sure. I'd love to talk. I've given this presentation for Scout Groups before and the models, so I would like to do that. Quickly on to Uranus. Now I know I'm just at my half hour, but let's go a few more minutes here. It's 1.8 billion miles. We're in the huge numbers here. My racquetball is 2¼ inches, and now we're going 2 miles away. So we just went a half mile, a mile, 2 miles, and now we get on to Neptune, similar size as Uranus, same size racquetball, but 2.8, another billion miles. That racquetball is, in orbit, 3 miles now from the sun. And then a quick look at Pluto. Pluto's tiny. It's smaller than our moon, and it is 3.7 billion miles away from the sun. And now this little pellet that's less than 3 millimeters in diameter, somebody discovered with a telescope sitting on Earth back in the early 1900s, and it's 4 miles away. Now we're getting serious here with some distances.
One scale I like to use is the length of your arm. If you take Mercury, Venus, Earth, and Mars, they will fit distance-wise on the nail on your finger. Then you have Jupiter is your knuckles, Saturn, Uranus, Neptune, and Pluto's on your shoulder.
Oh, nice. That's a good way of thinking about it. And then wrapping up, I guess, the furthest man-made object from our solar system, you're talking Voyager 1 probe. It was launched 43 years ago in 1977, and that probe is traveling at 38,000 miles an hour right now. So it's been up in space for a long time, and it's going fast. And you're like, oh, okay, well, how far away is it? It's far. It's 14 billion miles away. So Pluto was 3.7 billion. So, we're getting into, it's about almost 4 times as far away as Pluto. But on my scale, it's 15 miles, just over 15.5 miles. And it's like, wow, that's pretty far away. It's kind of at the edge of the solar system, maybe, right? It's like, no, the sun I talked about earlier is a light year away. On my a light year is just, you can't comprehend it. It's 15.9 trillion miles. On my scale, it's 6,543 miles. So you're going a quarter way around the world if you go circumference-wise to get from our spot here in Detroit to somewhere in China, going 1 light year. So if we're like, oh, well, when's Voyager going to get to the next closest star? Well, that's Proxima Centauri, and that's over 4 light years away. So you're talking, 5.9 trillion times 4. So if Voyager was to fly, continue on its path, if it had a direct shot, it would take 76,000 years still to get there. So basically, it's been flying for 43 years. It might as well have just been launched because it still has another 76,000 years to go. So Proxima Centauri on my scale, like I said, it's almost 28,000 miles away. So if you left Detroit, you flew completely around the Earth to Detroit again, and you were heading west, then you went again, and you kept on going, and you went to California, then you fly another 500 miles into the ocean. So that's our next closest star in our area. So I'm going to stop sharing real quick, and then we're going to just zoom quickly in on my little model. Actually, let me just show you Proxima Centauri. Talked away from my speaker. So Proxima Centauri right here is a basketball. And you can see, compared to the sun, it's not much of a star. But there's other stars in our solar system called red giants, and like Betelgeuse is a popular one in Orion. If that sat in the middle of our solar system, the edge of Betelgeuse would go all the way out to Jupiter. So what did I just say? It's a half mile away. So I literally need to get myself a beach ball that's a half mile in diameter, and seeing that in 3D,
in radius. In radius.
The radius, yes, the radius.
Yeah, a mile in diameter. Yeah.
Yeah, a mile in diameter, but the radius. So, so here's the model again. If you want to zoom in for me, my cameraman, and again we have Jupiter here, little basketball. I mentioned about the rings here. So as you can see, the rings cover outside Jupiter's radius. This way, you can see the size difference. And then again, like I showed you earlier, you got the Earth and the Moon. So I hope, I know I ran a little long today, but I appreciate everybody who came out tonight to take a look at this presentation. It will be on YouTube, so share it with a friend, or if you are interested, Liam did post our email. We're also the FordAstronomyClub.com. And then I think Liam probably posted the Survey Monkey if you want to take a survey. Give us some tips on how what you thought of tonight. And I hope you join us for everybody else's presentation from our club later on this evening that Liam mentioned at the beginning.
Yeah. I'll just quickly mention them.
One quick Proxima Centauri comment, if I can. Don't feel too sorry for it. Our sun has a life expectancy of just about 10 billion years. It's gone through about half of its fuel. It has about half as much again to go. Proxima Centauri, its life expectancy is 4 trillion years. that is with a T.
Yes, that's correct. That is
it's crazy.
Smaller, right?
So just quick reminder, the events that there's lots of events going on for us this evening, but the ones that our club is specifically doing, at 8:30 we have Tim Campbell, who just talked about Proxima Centauri, and myself, and we're going to be talking about spectroscopy and how we use light to discover what stuff is made out in the universe. And then straight after that, we will be going into a live Astronomy For Everyone TV show, broadcasting live here. I will be recording it as with
John McGill.
John McGill, sorry, my brain. With John McGill, and John McGill actually does NASA rocket launch photography. We're taking photos of the rockets as they're starting to launch. So we'll be talking about that. And then immediately following John, we'll be going in with Gordon Hansen, who, based on the weather right now, will may be doing live sky imaging, or may actually be showing you how he processes images after taking the photographs through his telescope to prepare the really beautiful images that we see out there. So we hope to see you back at 8:30, and enjoy the rest of the evening, and have a good evening. Thank you.
Thanks, everybody. Thanks for joining me tonight.